So we're going to launch 8.1. So while we're recording, we might as well say hi to Edson and Kaylin. Hi. Okay, we hope that you guys are listening and watching to this after you've just beaten Heritage. So that's what we're hoping for. Okay, we're rooting for you guys. Okay, so chapter 8. Yeah, short and sweet chapter. Just have a couple key points to get through. And we move on. So today is really kind of a backtrack day. We're not going to do anything that, we're not going to do derivatives or integrals yet. It's kind of like day 1 we talked about parametrics, and then day 2 we talked about the derivatives of parametrics. Same thing, vectors, we did a review day of vectors and then derivatives and stuff. So today is the review day on sequences. You start learning about sequences all the way in Algebra 1, and you dabble with them a little bit in Algebra 2, and then you do them in HAM, and then you guys haven't thought about them for a couple years now. So we didn't do anything with sequences last year in AB. So we just need to pull back what sequences are and what different types they are. So a sequence is just a list of numbers that follows a defined pattern. We're going to talk about the differences between arithmetic and a geometric, and then we're going to define what it means to be convergent and divergent. Okay, and any of you, I don't know, I'm just gonna, not to insult the boys, but you probably haven't read the Divergent series books, but have either of you girls read the Divergent series books or watched the movies? When you watch the movies, the books are way better, but just a shout out for those. Okay, so here we go. A sequence is a list of numbers that follows a prescribed order. So you're given a starting value, and then you're given some kind of pattern. The pattern can be defined as an additive pattern. It can be defined as a multiplicative pattern. It could be a pattern of powers. It can be a pattern of logs. But some pattern, and that is what we call a sequence. We define it with brackets, and we use the notation A sub n anytime we're talking about a sequence. So we'll be using that notation quite a bit, the letter A and the subscript in n. The n is the number that describes the position in the sequence that it is. So A sub 1 would be in first position, A sub 7 would be in 7th position, etc. So that's the nth position of the term. If the sequence ends, we call it finite. If the sequence does not end, then this is what I want you to do. You do a ... with ellipses at the end to show that it is a sequence that progresses according to the pattern without end. So we have both finite and infinite. So we don't use the infinity symbol to show that a sequence is going on forever. We use what's called an ellipses or a ... Okay, any questions about that? Okay. The major vocab that you should know before coming to this class, but you may have forgotten, is the difference between explicit and recursive. So an explicit sequence, that the pattern is based on the n value okay, or nth value. In other words, if I ask you to find me the 18th term, then you plug in the number 18 into the pre-described formula, and then you'll have the value, the 18th term. So it's dependent on the placement in the sequence that it is. That is explicit. It means you can jump directly to that term in the sequence. Okay, it's very easy to hop around from one term to another if you know what position it is. So let's do the nth value position, and it's simply a plug-in. A recursive has advantages, but it's a little harder to define because a recursive, the pattern is based on the previous value. So it has nothing to do with the fact that it's in the third position, other than you have to know what the second position value was in order to find the third. So you do something to the second value. And then to find the fourth, you have to do something to the third value. So you actually have to look to the previous term. We define a previous value this way, A sub n minus 1. That just tells you that you're looking to the term immediately prior to the nth term. So A sub n is dependent on A sub n minus 1. That's another way to write it. A sub n depends on a sub n minus 1. It's like, okay, I got to look at what I did last year, and then that impacts what I do this year. You're just looking prior. That is called recursive. In English, what does recursive mean? To like recurse something. To repeat it, okay? To repeat it on a cycle, to go back and like regurgitate it over and over and over again. Okay, this is an explicit sequence where I'm asking you to find the first 4 terms, and then I'm asking you to jump to the 100th term. So the way you would show that is you would just do A1 equals A2, A3, A4, and then you would jump to A100. Okay, explicit means you can jump and skip a big gap. In a recursive, you can't do that. If I asked you to find the 100th term, you'd have to know the 99 terms before that. But in an explicit, we can. So a sub 1 means I'm going to plug the number 1 into the nth position. So that would give me negative 1 to the first over 1 squared plus 2. So this is basically like finding a function. The numerator is negative 1 and the denominator is 3. But the fact that that value turned out to be negative 1/3 doesn't impact the next value. The next value is independent of that, as opposed to recursive, the next value would depend on that value. So this is an independent explicit sequence. So the next one would be negative 1 squared, and then over 2 squared plus 2. So then that pattern would be a positive 1 on the top, and then 6 on the bottom. A pattern will start to emerge as you work through this explicit value. When we do a sub 3, it'll be negative 1 to the third over 3 squared plus 2. All right, so what about the pattern are you starting to notice already? Okay, what about what's happening in the numerator at least? Like sometimes it's easier to say the numerator follows this pattern and the denominator follows that pattern. So the numerator is going to be back to what value? Negative 1. It started out as negative 1, then it changed to positive 1, now it's back to negative 1 again. Okay, and the denominator is now 11. Negative 1 to the fourth over 4 quantity squared plus 2. Now we're back to positive 1, and then now my denominator is up to 18. So you might be asked to describe the pattern that you see, and it's usually easiest to identify a separate pattern for the numerator and denominator. Don't look for a pattern altogether. Say the numerator is following an alternating pattern. It's alternating from positive 1 to negative 1 and back and forth all the time. So every odd nth term is going to be negative. Every even nth term will be positive. Okay, the denominator. See if we can figure out if we're noticing a pattern about that. We've got 3 changing to 6, changing to 11, changing to 18. Anything you notice about those numbers? What direction are they going? They're increasing, right? The denominators are increasing. The terms themselves are getting smaller because the denominator gets bigger. But as we go from 3 to 6, what's the jump? From the number 3 to 6. 3, okay? As we go from 6 to 11. As we go from 11 to 18. 7, okay? So could you interpret a pattern from that? From 3 to 6, from 6 to 11, from 11 to 18. So we're going up by 3, then up by 5, and then up by 7. So if you were to predict what A5 was without following a pattern at all, what would you say about the numerator? Negative 1. What would you say about the denominator? It is 27. And you could check that. It works out. And you can predict the next one, and the next one, and the next one. All right, but we could also jump. We can jump right to A of 100. So we know that the numerator of A of 100, A sub 100, or the 100th term, is going to be positive or negative? Why positive? Not it's a positive power. All of them are positive powers. It's an even power, okay? It's an even power. So we would have -1 to an even number. So that would give me an even value. And then my denominator is going to be 100 quantity squared plus 2. So that'll give me a positive value. And then 100 squared is 10,000. And then I'll add 2. So I'm going to get 10,002 as my denominator. So that's a sample of an explicit formula where you can just find values by plugging in the position that that term would fall into. Typically, we would write our answer maybe something like this: -1/3, comma, +1/6, comma, -1/11, comma, +1/8, comma, dot, dot, dot. And then later is going to come +1 over 10,002, and then dot, 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 and this keeps going. So you would write it like that. Sometimes you'll be given just that. And they will ask you, if that's the pattern, what position is that? And you have to work yourself backwards and try and figure out what position that falls in. I'll show you how to do that. Okay, but this is in the 100th position. All right, next one. Okay, recursively. You know you're working with a recursive sequence when you have this n-1 pop up right here. N-1 again stands for the term immediately prior, the previous term right before the one that you're working on right now. And so here, if it's asking us to find the first 3 terms and the 7th term, unfortunately this is like a question in disguise. You can't just jump to the 7th term. Yes, I asked you to find the first 3 terms, but what else are you going to have to find? You're going to have to find the 4th, the 5th, and the 6th as well before you can find the 7th. In a recursive, there's no way to jump from one to the other. So this is actually asking you for all 7 of the terms. But you should notice a pattern emerging pretty quickly once you get the first 3 down. All right, so A1 is given, oh, sorry. These are all B's. I apologize. Let's fix all that. This was defined as the B sequence. All right, so this is B1, B2, B sub. All right, so B sub 1 is given. In a recursive sequence, you have to be given the first number because otherwise you don't have anything to work with. So you were starting with number 4. The second term, according to the formula, says go to the term before, the term that you just did, and then subtract 2. So it would be taking that term of 4 and subtracting 2 from it, and then we end up with 2. And then to find the third, it says, okay, take that one and subtract 2. So that gets me down to 0. Okay, take that one and subtract 2, and that gets me down to -2. But now you can pretty easily see this, that the pattern of this is just emerging as a subtraction pattern, going from 4 to 2 to 0 to -2. So you can get your way through without too much trouble down to the 7th term, which is -8. One of the most famous recursive sequences is the Fibonacci sequence. I just want to add that in here. Leonardo Fibonacci. His sequence was formed by defining the first 2 terms. He defined terms 1 and 2. He defined them as both being the value of 1. And then his formula for all others was a sub n equals a sub n minus 1 added to a sub n minus 2. So in layman's terms, what Fibonacci was saying is in order to create my sequence, I'll give you the first 2 numbers, and then after that, I want you to add the 2 numbers together to make the next number. Okay, add the previous 2 numbers together and get the next one. So A3 would be the sum of the first 2. So 1 plus 1 is 3. And then A4 would be the sum of the two before that. Excuse me. Thanks, Alex. 2. Okay, then A4 would be the sum of that one plus the one before it. So that would be 3. And then A5 is the sum of the one we just got plus the one before that. 1, 1, 2, 3, 5. And then 5 plus 3 is 8. And 8 plus 5 is 13, and et cetera, et cetera. This is called the Fibonacci sequence. And this was Fibonacci putting a formula to something that was observed in nature. This pattern, 1, 1, 2, 3, 5, 8, 13, 21, 35, it just keeps going by adding those two terms together, okay, shows up so many different places in nature. So Fibonacci was studying what happens. He was studying the number of sunflower seeds in a sunflower, and it was always one of these numbers. He was studying the number of spines on a pine cone, like the little pointy things on a pine cone, counting those, always one of these numbers. Counting the spirals on a snail shell, and the spaces in the spirals we're measuring, always these numbers, okay? Amazing how many different natural occurrences of Fibonacci sequence there were, and his observations then led him to create this pattern. I need to be able to formulate something, so he figured out the mathematical formula for Fibonacci sequence. So it's a beautiful sequence. All right, so how do you create formulas for other sequences? If you know that it's an additive pattern, then we call that an arithmetic sequence. Okay, so when I think of a pattern of addition, I think of the letter A, and so arithmetic sequences always follow an additive pattern. Of course, this actually applies to subtraction as well, because subtraction is just fancy addition. Subtraction is adding negative numbers. So we count addition and subtraction in the same category as an arithmetic sequence. The gain from one term to the next is called the common difference. So this common difference right here is the gain or loss between terms. Think of it like the slope. In the slope of a linear function, you're either gaining, rise over run, rise over run, rise over run, or you're losing and you're falling, fall over run, fall over run, fall over run, as on a constant pattern. That's the same thing as the common difference. That common difference is multiplied by n minus 1 and added to the previous term. So this is how you would write an arithmetic sequence, is that you have a sub n, so any term can be found by taking the first term and then multiplying it by d times n minus 1. So d being that gain or loss. And you do that one fewer times than the term you're looking for. If you rearrange those, it looks like this. You might okay, so if I just rearrange those terms, if I rearrange that, it looks like this. Does that look like anything you've ever seen before? Say that again? It is the same as point slope form. It's y2 or y minus y1 equals m times x minus x1. It's the exact same. An arithmetic sequence is just a linear formula. D is the same as m. The common gain or the common difference is the same as the slope. n is the same as x. Y is the dependent variable. So the connections are the same, the terminology is different. All right, so if you're supposed to turn this into an arithmetic sequence, a formula, you just need to identify what is the common gain from one term to the next. So as you're looking at these, what do you identify that as? Is it a gain or a loss? A gain of how much? 4. Is that consistent every time? Okay, so D is 4. And so we want to come up with a formula that would represent that. So A sub n equals, or that's Y equals, it's the exact same. Okay, if you want to think of it that way, if you want to think of it as Y minus Y1 equals MX minus X1, you can think of it that way. This would be Y minus, the Y value is -3, that's the first Y value. And then 1, 2, 3, and 4 are the X values, if you think of it like that. So you're looking at 1, -3 being your position. So that would be 4 times X minus 1. That's exactly the same. Y plus 3 equals 4 times X minus 1, or Y equals 4 times X minus 1 minus 3. Or if you're putting that in explicit notation, A sub n equals 4 times n minus 1 minus 3. Same thing. That's the notation. We just swap the y's for the A sub n. We swap the x's for the position of n. So that would be called the explicit rule. And if you want to find the 9th term, you just drop the number 9 in for the nth value. So A sub 9 would be 4 times 9 minus 1 minus 3. In other words, 32 minus 3, or 29. You could also find the nth term just like, what would an elementary school student do if I was asking them to find the 9th term? They'd just probably keep taking the pattern and go plus 4, plus 4, plus 4, plus 4, and that works too. It's just if I ask you to find the 72nd term, it's going to take you a long time to do that, so it's easier to have a formula that you can jump around. Okay, any questions on arithmetic sequences? A geometric sequence is following a multiplicative pattern. And we group division in this as well, because just like subtraction is fancy addition, division is fancy multiplication. Division and multiplication are grouped together in this same thing, because if you're going to divide by 4, you might as well multiply by 1/4. It can be expressed similarly. The gain from one to the next is called the common ratio. And the ratio would never be said, like you would never say, the ratio is to divide by 3. That's not the rule. You wouldn't say divide by 3. You would say multiply by 1/3. So it's always multiplication. They call that the R value. R value coming from the word ratio. And so the format here would be any nth term is found by multiplying or taking the ratio and raising it to the n minus 1 power and multiplying it by a sub 1, by the first term. So the first term and then multiplied by r to the n minus 1. I want you to look at the commonalities here. Both of them have an n minus 1. Both of them start with a sub 1. But the key differences are that even one of them has a sub 1 started with and then multiplied, and the other has a sub 1 added. So that follows the pattern. If Arithmetic, you're going to add. If it's geometric, you're going to multiply. And then both of them take this gain that you're having and do something to n minus 1 to it. Either you're raising it to a power, which is what multiplication is. If you're multiplying by 4, then multiplying by 4 again, and multiplying by 4 again, and then multiplying by 4 again, that's 4 to a power. Or you're multiplying the reiteration. Okay, so let's try this here. For a geometric sequence, find the common ratio. All right, so as you look, you can clearly see that something's going on with the number 3 here. Multiplying by 3, multiplying by 3, multiplying by 3. But what else is going on, Jonathan? Besides just multiplying by 3, what else is happening?
It's changing between negative and positive.
So what kind of multiplication would I be doing here?
-3.
Right, I'm multiplying by -3. So the common ratio for this one is that r is equal to -3. So the explicit rule is going to follow that multiplicative pattern. So my nth term would be start with a sub 1 and then take whatever r is and raise it. So in my case, my a sub 1 is the number 1. My r in parentheses is -3. And then n minus 1 is the power. So that becomes my explicit rule for any term in the sequence. So if I want to jump to the 10th term in the rule, then a sub 10 still starts with the number 1. It takes -3 and it raises it not to the 10th power, but it raises it to the 9th power. Because in order to get to the 10th term, you had to have multiplied by -3 9 times. Okay, so -3 multiplied, -3 multiplied again, -3 multiplied again. And so 3 to the 9th is, or -3, is 19,683. So these get big really fast when you're talking about powers. All right, so suppose you have to construct the sequence yourself. Suppose you aren't given a nice list of numbers, but you're given them kind of broken up. You have the 2nd and the 5th. Okay, so we say, all right, we don't know what A1 is. We know that the second one is -6. We don't know what A3 is. We don't know what A4 is, but we do know that A5 is 48. How would you figure out the common ratio? So you don't know A1 and you don't know that common thing. Okay, we can finish this. So you're going to set up 2 and solve them simultaneously. I don't know the first term. I don't know the r term, but I do know that when you raise r to the first power, when you've done the first multiplication, you should get -6. So you've done one multiplication, and the second term should be -6. I also don't know the first term, but I do know that once I've done 4 multiplications by r, I should arrive at 48. That is called a simultaneous algebraic system, and you should be able to solve that by solving for one variable and substituting. Get one variable alone, and then solve for the other. To me, it looks like it's easiest to get A1 alone. How would you do that? Divide by r. So that would turn into A1 alone being -6 over r. Then what do you do with that? Plug it in where? Yeah, plug it in to that A1. So we're going to have 48 equals -6 over r times r to the 4th. And then you just solve that. So that can be reduced to -6r cubed. And then you can solve by dividing. Divide both sides by -6. Cube root both sides. R turns out to be -2. So that's how you can solve for the r, even if you aren't given it in the first part of it.